The Cavendish Laboratory has a long history in the physics of energy. Important milestones include Rutherford and Chadwick's pioneering work on nuclear fission in the 1930s, Richard Friend's discovery in the early 1990s of novel molecular or plastic semiconductors, or David Mackay's influential book on sustainable energy without the hot air. Now more than ever, physics has an important role to play in addressing the urgent challenge of climate change. Physics helps us to better understand and improve the physical processes involved in energy conversion, energy storage, and energy use. Physical methods and insights can lead to the discovery of disruptive new materials that enable technologies needed for the transition to sustainable energy systems. This is what brings together researchers in the energy materials theme in the Cavendish.
The development of new materials and technologies which is going to assist the energy transition does not rely on a single discipline. The Cavendish Laboratory and the Yusuf Hamid Department of Chemistry work very closely so that when new materials are made and developed, they can be studied quickly and then their physics understood at a deep level. Importantly, it's the interaction of the people and the scientists that come together to develop new ideas, new technologies, new materials, so they can overcome the current bottlenecks and develop new technologies for a greener future.
Here in the UberFast lab, we use many different advanced spectroscopy and microscopy techniques to probe material properties trillions of times a second. This helps us understand new materials useful for the energy transition, such as solar cells or LEDs.
Energy storage is a really important part of the energy transition. As we move to renewables, we need to be able to control supply and demand, and energy storage allows us to do that on the grid. In my research group, we're developing materials for new types of rechargeable batteries. We look at developing novel materials for current technologies such as lithium-ion batteries, as well as next-generation battery technologies, including sodium-ion and magnesium-ion batteries.
I'm involved in a research program that developed novel thermoelectric materials that convert heat, which would otherwise be wasted, into useful electricity. To better understand the underpinning physics of these materials, one of the techniques we are using is to scan the tip of an atomic force microscopy across the surface of the material and also probe the charge and heat transport processes on the nanoscale.
So in our lab, we're very interested in magnets because magnets have been for the past 100 years and still are today what we use to store digital information for a long period of time in data centers, for example. But to write and read this data, we need to use a very large portion of the energy production. So we're looking now for new physics and materials that would allow suppressing the energy costs and increase the speed with which we write and read the magnetic data.
In this lab, we investigate how to store information in magnets at very low temperatures, below -260 degrees Celsius. Memories that can work under these conditions are required before technologies such as quantum computing can really flourish, but their integration will require to reduce their energy consumption. We think that by exploiting the rich physics at the interfaces of superconductors and magnets, this can be achieved.
We are living at the cusp of a very exciting time. If we think about the history of the world, for thousands of years we had access only to basic biofuels and animal-driven energy sources. This all changed in the 18th century with the Industrial Revolution, which brought about new sources of fuels, fossil fuels, which changed the course of human history. But today they've also brought us to the brink of environmental disaster. The challenge in front of us now is to create the green transition to a new age of ultra-low cost and green energy. This is a really exciting time, and we here in Cambridge are energized by this mission across multiple disciplines. And we see that physics sits at the very heart of this, developing the basic physical concepts, the new devices, the new characterization technologies that will drive this transition.